job. All right. So thanks everyone for joining this Zoom talk. So Luca Pinol is gonna give the talk, and this is indeed, as we were saying, the talk with which Luca presents itself to the IFT. Of course, because of the pandemic, it has not been possible to do it in person. And as most of you already know, of course, Luca got his PhD at IAPE, and he's recently joined us at IFT working on, I would say, a lot of topics, but all of them fit within early universe physics. And it's a pleasure to have him here with us. And today he's going to tell us about geometrical aspects of inflation, stochastic inflation in particular. So please go ahead, Luca.
Thank you, Matteo. So yes, good afternoon, everyone. I'm very glad to present to you my new institute since this September, part of my research work. So of course, I would have preferred to see you all physically in the conference room. That would have been much funnier, but actually I have COVID, so it's better for you that you are not there with me. Actually, if you want to turn on your camera, don't hesitate, but you're not forced neither, of course. And so yes, in this talk, I'm going to talk about stochastic inflation, which is a way to describe the large-scale fluctuations during inflation in a non-perturbative way. So the rough idea will be that instead of the background, which is in the slow roll for a usual picture of inflation, we'll have this the non-deterministic description of the large-scale fluctuations, which will be therefore stochastic. So just before going on into the details of the seminar, I just want to warn you that the seminar will be a bit technical, but I hope in the good sense. I mean that it does not require much prior knowledge. In particular, I hope that it is as much understandable as by non-cosmologists than by cosmologists. And it is built a bit like a lecture, so it's building on what I will have presented in the previous slides. And just to mention to you other directions of my research that actually are most part of my research that I don't have the time to present all here. So I have worked a lot on primordial non-Gaussianities, and in particular in the context of multifield models of inflation that we will also encounter during this seminar. Here at IFT, I am working mainly with Matteo Faziello about primordial gravitational waves and how they can be emitted during inflation. And I also have some expertise on the reheating mechanism that takes place between the end of inflation and the onset of the radiation and the matter-dominated eras in cosmology. So this is the outline of my talk. So we'll begin by very briefly reviewing the usual picture of inflation. And then I will go into the heart of what is stochastic inflation and some concepts about stochastic differential equations. So this will be largely the longest part of my talk, actually. So it's kind of a long introductory section, but actually a big part of my research on these topics were to understand those things. So I'm happy to explain them to you. And then the third part will be really about the new results that we got in the last 3 years with my collaborators. The fourth part, unfortunately, I won't have the time to present it, but I will just flash you in one slide what is the spirit of the path integral derivation that we used to have this so-called Langevin equations for the multifield setup of inflation. So first, the standard picture of inflation. So let me be very brief about this because I'm sure you all know this, but the very basics is that it is the observation of the cosmic microwave background that actually motivated the introduction of inflation as a theory for the early universe. So the idea is that we see that our universe is correlated on scales which are extremely large at a very early stage of its history. And this can only be explained if there was a sufficiently long period of accelerated expansion in the early universe, which enables to solve this so-called horizon problem. And you can also define other problems that are solved by this accelerated expansion, such as the fine-tuned value of the spatial curvature. So this is a very important sketch of the evolution of the relevant scales in the early universe. So the point is that during radiation domination and then matter domination, the co-moving Hubble radius, cal h-1, is increasing. But if you want to solve the horizon and the flatness problems, you need it to be decreasing at some point. And this is exactly what does inflation. Inflation is a period of decreasing co-moving Hubble radius. So what's very important, therefore, is that if you look at physical scales, such as these 3 long, middle, and short scales here, is that before being stretched on the superhorizon scales and giving the anisotropies in the CMB, for example, they were once inside the so-called instantaneous horizon here. And therefore, they emerge from small quantum fluctuations that are then stretched on the superhorizon scales. This is a history, I mean, this is a sketch of what inflation does for perturbations. So what is the usual mechanics that is invoked to explain this epoch of accelerated expansion and these quantum fluctuations? Well, the simplest thing to do is to suppose that the matter content of the universe was dominated by a single scalar field, which has a potential, and this potential must be sufficiently flat so that the scalar field is actually rolling down the potential, but at a very small velocity. If this happens, then you have an almost exponential expansion of the universe, which means a decreasing co-moving Hubble radius. Then, on top of this, you need to have quantum fluctuations. So we'll have this homogeneous background, which is in slow roll, plus some quantum perturbation, which can have some spatial as well as time dependence. The quantum fluctuations, you need to have some prescription for their initial conditions. And the simplest thing you can think of is called the Bunch-Davies vacuum. It is basically the most straightforward generalization of the usual flat space-time vacuum to this context. So with those two ingredients, a homogeneous background in slow roll plus some quantum fluctuations that are initialized in the vacuum, what you derive, what's your, okay, that was the quantum fluctuations. What you can derive is the power spectrum of the curvature perturbation zeta. And if you do the computation, what you will almost always encounter with this hypothesis is an almost scale invariant power spectrum. So it is a power law with a spectral index, which is very close to 1. And then depending on the models of inflation, you will have slightly different values of NS, which will enable you to discriminate amongst models of inflation given the observed value of NS, for example, in the experiments. Okay, so that was a bit quick, but this is because I want to go to actually stochastic inflation, which is quite different. So the previous picture does pretty well when you have this cosmological perturbation theory, which is a homogeneous background and some small fluctuations. But this may not always be the case, actually. So actually, if the potential is extremely flat, then the classical dynamics that you derive from the potential is actually quite weak. And the effect of the quantum fluctuations may actually be greater than the one derived from the classical potential. Also, even if at each time step, the quantum fluctuations are actually of smaller amplitude than the classical force, they may accumulate over very long time scales and at the end produce an effect which is bigger than the classical drift. So in that case, what happens is a phenomenon of what we call diffusion, which is that instead of having a good delimitation between the large and the small scales, the effect of the small scales will backreact on the largest ones. And actually, to describe accurately the dynamics of these large scales, you cannot have this cosmological perturbation theory anymore. You need to have something which is non-perturbative to describe the large-scale fluctuations during inflation. So if we allow to have such large-scale fluctuations during inflation, then we will not be able to consider a homogeneous background anymore. So we'll have to divide our scalar field into an infrared sector, which we will describe the large-scale fluctuations, and a ultraviolet sector, which will be about the very small-scale fluctuations. So now the decomposition of your scalar field is in this infrared and ultraviolet sectors. So you will still assume that the ultraviolet sector has smaller amplitude than the infrared one. And you will treat the small-scale fluctuations still in perturbation theory, but the infrared ones, you would like to keep a nonlinear treatment of them. Okay, you don't want to expand in powers of phi infrared. You want to have a fully nonlinear theory in terms of the large-scale fluctuations. So technically, how can you do that? Well, what you are aiming for is called an effective field theory for the large scales by integrating out the ultraviolet one. So this is called the coarse-graining procedure. And it is something that is like the basics of physics, to basically look at the scales which are relevant and to integrate out the ones that are not. So we will do this expansion, and we will also take the opportunity that infrared fields by definition have small gradients to simplify the equations. So what we should find is actually a stochastic description for the infrared part of your scalar field. And so let me explain you why. So the idea of stochastic inflation is that the quantum effects will backreact on the larger scales. And therefore, we know that the outcome of quantum processes can be described by us observers as stochastic processes. And therefore, at each position of space in the universe, you will have different realizations of those quantum processes, which you will measure as different realization of stochastic processes. And therefore, the value of your scalar field at large scales around this point will be actually a stochastic variable itself. And therefore, if you look at different patches of the universe with very large distances between them, you will find that there are different amplitudes of these large scale fluctuations. And since this amplitude is stochastic, what we should expect to see is some kind of Brownian motion for our infrared sector. And the tools to describe those stochastic processes are mainly the Langevin equation and the Fokker-Planck equation that we will both encounter in the following. So let's go back to this plot of the evolution of scales during inflation. So this green plain line is still the co-moving Hubble radius. And the point is that scales cross this co-moving Hubble radius at some time that depends on their actual wave number. And what we would like to do is to define our UV and our infrared sector. And for this, we'll have to define a cutoff, okay? And actually, since this co-moving Hubble radius is the only scales that we have at hand during inflation, we must define it with respect to this horizon scale. And so what we will do is that we will not take exactly the co-moving Hubble radius as being the cutoff scale, but we will take a scale which is a bit larger in physical space, in order to have in our infrared sector, so the one that is above the scale, only fluctuations which are on typical scales that are much larger than the horizon size. And this is because we want to treat our infrared fluctuations as being classical, although we will see random, but still classical variables. And we know that deep inside the horizon, the right treatment of the fluctuations is actually a quantum treatment. So there must be, at some point around the horizon crossing, a process which is called classicalization, and which is the process by which the perturbations go from quantum to classical, because we do observe classical fluctuations in the CMB and in the large scale structure. So to be safe, we'll take some scale which is larger than the horizon size, and this how much larger is quantified by this parameter sigma, which is much smaller than 1. So the crucial point is that this definition is not static. Because the co-moving Hubble radius is decreasing, you see that at different times, your infrared and your ultraviolet sectors are different. So as time passes, actually, you have more modes that come from the UV sector and that go into the infrared. So that means that within your UV sector, you see that the infrared sector is actually growing and taking much more space in the space of wave numbers. So therefore, if you want to describe this infrared sector, what you're actually describing is an open system out of equilibrium and that receives contributions from the ultraviolet sector at each time step. So now we would like to go a bit more into the mathematics of this concepts that I have defined here. So what we are doing when we split our scalar field into infrared and ultraviolet parts is that we decompose them in Fourier space. And the easiest thing to do is to just add a window function in Fourier space to separate the small and the large scales. And here, small and large are defined with respect, again, to this cutoff K sigma, which is proportional to the co-moving Hubble parameter. So the easiest thing you can think of is just a step function, which will select the smallest wave numbers for the infrared part, for example. Now, if you plug this ansatz into the equations of motion that you can derive from your Lagrangian, what you will find, assuming some still slow roll hypothesis in order to be just for simplicity at this point, what you will find is that you will recover the classical drift, the one that you have for the background, the homogeneous background in the usual cosmological perturbation theory. So this is the usual slow roll term, but you will recover also a second term that will be proportional to this mode function in Fourier space of your fluctuating field and to the derivative of the window function. And the derivative of function that looks like a step function is basically a Dirac delta. So it means that on top of the classical drift, what you will get is a contribution that is proportional to your wave function at this particular scale, which is the cutoff scale at this time. So it means that you have some power that goes into your infrared sector and that comes from the UV sector that joins the infrared sector at that particular time. And this is how you should interpret this new term that, as we will see, we will interpret actually as being a noise. So this is the equation that we get, and which is actually the Langevin equation. It is a Langevin equation because this new term, psi-phi, is actually interpreted as a noise. Let me explain you how. So actually, to be more precise, I remind you that the correct treatment of the fluctuations during inflation is that they should be quantized, at least initially. So actually, when we see a mode function phi of k, it is not a function. It should be understood as a quantum operator. So here, actually, this is an operator equation, if we want to be completely rigorous. And actually, the quantum operators during inflation, they can be decomposed into the usual annihilation and creation operators with some wave functions, phi k, which this time are really functions and not operators anymore. So this is the usual mode decomposition of the scalar field during inflation. But now remember that the derivative of the window function actually selects particular wave numbers. It's not any wave number that appears in this equation. It is only the wave number which is at the cutoff scale, and which shows the cutoff scale, such as this wave number represents a physical scale that is much above the horizon. And remember, we did all this because we wanted that the mode that the infrared sector is well classicalized. So somehow this quantum feature should not be there anymore. And indeed, this is what we see, because if you replace the wave number k by k sigma, and you just look at what are the wave functions of this particular mode at this time, actually, you can show that they converge to a real quantity. So the function becomes real on the superhorizon scales. And if it becomes real, it means that, well, the complex conjugate is actually the same as the wave function itself. And therefore, what you can do is that you can factorize this expression, and therefore your quantum operator becomes actually just a function times the sum of the creation and annihilation operators. So therefore, at this time n, the only quantum operator that you are left with is actually the sum of the creation and annihilation operators. And therefore, it is the only operator that remains in your theory, and it therefore commutes with all other operators because it commutes with itself. And therefore, you see that the quantumness of the phi k mode is somehow lost on superhorizon scales. Actually, let me say that this is all something which is something that you are going into this direction, but there is always a small commutating part, but it just becomes increasingly negligible as your mode go above the horizon. But therefore, you can define B as being the sum of those two quantum operators, and you see that this B is the only remaining operator. And then you can look at the statistics of B. And if you do so, knowing the statistic of the creation and annihilation operators, which is the standard one, you can derive that B has zero mean, and it is actually a Gaussian random variable. It has a two-point function, which is basically 1 in the good units. So your new term here, psi-phi, is actually a Gaussian random variable, and it is classical in the sense that there is no commutator, no non-trivial commutator anymore. So now you can compute what is exactly the statistics of this psi term, which you derive from the statistics of B, which is trivial, and all these things in the equation, but you can actually compute it analytically. And you find this result. So now I will explain you what are the different terms in this result. So first, you see that the noise at different times are uncorrelated. So the noise at the time n is not correlated with the noise at the time n prime if it's not the same time. So this is a feature that we call white noise. And let me just tell you very simply that this is actually a feature that comes from the fact that we chose a step function and that we have this derivative, which is exactly a delta function. If we had taken a smoother window function, we would have gotten what is called the colored noise, so slightly correlated in time noise. But mathematically, white noises are easier to handle, so we do this approximation, which is a priori well justified. Then we have actually some spatial correlation. Here, R is the physical distance between the 2 points, x and x prime. And this spatial correlation is cardinal sinus. Cardinal sinus, you know, is this function, which is basically 1 for very small value of the arguments, and basically 0 for large value of the argument. And here, very small and very large, again, is with respect always to this cutoff scale, k sigma. So it means that 2 points that are separated by distances much smaller than this cutoff scale are completely correlated. The noise takes the same value at these 2 points if they are at a distance less than the cutoff scale. However, for distances larger than the cutoff scale, they are completely uncorrelated. So this is important because it will enable us to make some approximation, which is the following one. So here is just a sketch of what would be the size of our universe today, for example, in black. And you see it encompasses many horizon sizes universes at that time during inflation that themselves can be grouped into these red patches, which are the cutoff scale, which is the cutoff scale here, which is larger than the horizon scale. And you see that the idea of this spatial correlation, which is 1 within this distance and 0 beyond this distance, is that you can basically focus on one patch statistics. It means that if you look at one patch, then the noise will take the same value everywhere in this patch. Then you look at another patch. Okay, within this patch, it will be the same value, but this value will be completely uncorrelated with the one of the patch, which is its neighbor. So this will enable us to simplify the Langevin equation. And instead of having a dependence on x, which was a continuous variable, which was the spatial position, we'll now have actually a dependence only on p, which is a discrete variable, which will be the number of the patch, if you want. So in each patch, you will have a different value of the noise and therefore a different value of your infrared field. But within one patch, it will be the same everywhere. So that's why we go from this cardinal sinus function here to this delta PQ Kronecker symbol, very, very simple. Then actually just for making the link with cosmology, for the one that know that, we can use the so-called separate universe approach to calculate the statistics of zeta, which is the curvature perturbation that then we can observe in the CMB from this approach by using the so-called delta N formalism. So let me not go into the details, that's just for a small remark for the experts. So let us go back to this noise statistics, and the remaining term here in green, is actually the amplitude of the noise. And the amplitude of the noise is actually the power spectrum of the ultraviolet fluctuations when they cross this cutoff scale. So this makes sense because it means that actually the power that is in the ultraviolet sector and that is transferred into the infrared sector, which is the system you are studying, is transferred. The power is transferred, and this is why the amplitude of the noise is just given by the power spectrum of these UV fluctuations at this particular time for this particular scale that changes from UV to infrared at that time. Okay. Now a small remark and beginning to go into the details of stochastic processes. So how do you do in practice? Well, in order to compute in order to evolve in time your Langevin equation, you need to know the noise statistics. But to know the noise statistics, as we've seen, you need to know the power spectrum of the UV fluctuations when they cross the cutoff scale. So what you should do is to first solve for the linear equation of motion verified by your mode functions. But this is not so easy because actually, if you look at the Klein-Gordon equation for this wave function, what you find is that it depends actually on the value of the Hubble parameter, which is the logarithmic derivative of the scale factor, and many things that depends like on the derivative of the potential, the second derivative of the potential, etc., which is encompassed in this effective mass term. And both of them actually depend on the value of your background, which is here a stochastic background in your patch P, which is therefore the background is completely stochastic here. And so therefore, in order to compute the statistics of the noise, well, you also need to know what's the value of the stochastic process at that time. And this is quite intricate. So in principle, you cannot solve the two systems separately. It's not like in cosmological perturbation theory. You cannot first solve for the background and then for the perturbation. You need to really be evolving both at the same time. So this is one complication. And actually what it implies, which is even more complicated maybe, is that the system is what we call non-Markovian. And what non-Markovian means is that the noise statistics at a given time depends on the realization that the noise had in the past. And this, I think you can see it here. For example, if you want to compute the power spectrum at a given time n, you need to solve this equation of motion. But in order to solve it, you need to know what's the value of h and m. And this is a stochastic thing. So it depends on your process. If you repeat the process different times, you will not always have the same value of the noise at the time n. So this is what we call non-Markovian. And it is, of course, a difficulty. So all this to say that actually, this is where really what should be stochastic inflation. It's very complicated. So of course, we would like to now have some approximation and some assumptions in order to simplify a bit all this and to be able to actually derive something physical. So a first thing to do is to make the approximation that your scalar field is massless. If you make this approximation, then you actually have some analytical formula for the power spectrum of your fluctuations. So it is well known that the amplitude, the typical amplitude of the fluctuation which are massless is h over 2 pi. But actually, if you really take into account the time dependence of your setup, and you look at the power spectrum at the cutoff scale, it actually depends on the value of the Hubble parameter at the time n prime, which is the time at which the scale exited the horizon. And n prime and n a priori are different. And here you see very well the non-Markovianness of your system, which is that the noise at the time n depends on the stochastic quantity at the time which is before that. Okay, that's life. Another approximation that you can add on top of this is that your background is actually slow varying. And this is something which is not too strong in inflation because we all want to have these slow roll parameters, epsilon, eta to be small. So if you do this, then the noise at the time, the Hubble parameter at the time n prime is almost like the one at n. And you can make the approximation that therefore the noise, the stochastic process is Markovian, because now the noise statistics only depends on function of the time n at which you evaluate the noise. But it's still what we call multiplicative because the Hubble parameter is a function of the stochastic process at the same time, but still a function of the stochastic process. That's what we call multiplicative noise. Now you can go to even more assumptions and suppose that actually your scalar field is not the inflaton, is not the one that is driving the background. And therefore the background, the Hubble parameter is not a stochastic variable. It is driven by something else. And therefore, now the noise statistic does not depend on the stochastic process. It just depends on time, maybe because you have some other process that makes the Hubble parameter time dependent. So this is simpler and it's called additive noise. And many difficulties disappear when you have additive noise. And then, of course, an even more simpler scenario, which is also interesting for deriving formal results, is to assume that actually the space-time is completely de Sitter. So there is no really an inflationary dynamics. It is an exactly exponential expansion. And in that case, the Hubble factor is just a number, h0, and everything is much simpler because the noise is just constant. So in the following, in general, we will assume that we have the massless scalar fields and a slow variation in order to be in the Markovian approximation. But unless otherwise stated, I will always consider a multiplicative noise, which is the most general Markovian case that we have at hand. Okay, so now we will go into what is called the Fokker-Planck equation, which is very important. So we focus on one patch, and therefore I will remove the P, which was for the patch P. I will always look at one patch, okay, the patch 1, and look at the Langevin equation that is verified by our infrared system. So we have this drift, and we have the noise term. Because we have a massless scalar field, we know the amplitude is just h over 2 pi, but because we are in the case of multiplicative noise, we see that h depends on the stochastic process. And here I have put out of the noise itself the amplitude of the noise in order to define this normalized centered Gaussian variable psi, which has now weight 1, if you want. And this is important in order to derive what is called the Fokker-Planck equation. And the Fokker-Planck equation is an equation for the probability density function of your stochastic variable. So therefore, you go from a stochastic differential equation to a partial differential equation, which is deterministic, for the PDF. And this is something that is well known in statistical physics and that you can apply to this Langevin equation because at the end, it's just a Langevin equation. So when you do this, this is what you find for your PDF P of your infrared sector. And at the time n, what you find is what's called the convection diffusion equation, which everyone knows from courses of classical physics. And we have a drift term, so one derivative with respect to the field, and we have a diffusion term, second derivative with respect to the fields. And the diffusion clearly comes from the quantum kicks that the infrared system receives at each time step, because you see this amplitude of the noise squared here inside the double derivative. Here we have the classical drift, which is just the usual slow roll dynamics. And here we have a new term, which is a bit weird, which is called the noise-induced drift, and which will be important. I will come back to it in the following, and in particular about this parameter alpha that does not appear here explicitly, but however is in the Fokker-Planck equation. So we are back to this small animation. So what convection does, well, it pushes the center of your PDF towards the minimum of the potential. And what is doing the diffusion? Well, it just spreads your PDF to larger values, allowing for more exotic, if you want, values of your infrared fields phi. So this is why you will be able to describe, for example, very large value of your infrared fluctuations with this stochastic formalism, which you could not do in the context of cosmological perturbation theory, because you were always expanding in a very close neighborhood of your classical trajectory. So let me go back a bit more general and now start the course on stochastic differential equations. So this is a very general Langevin equation, okay, still for our variable phi infrared here, with a drift term h and with a noise term g, which is multiplicative, which is a case of interest for inflation. How do you solve that? I mean, how do you do things? How do you derive anything with that? Well, you can try to solve it numerically, for example. And if you do this, what you will have to do to solve it numerically is that you will have to define a grid of time, right? And you will need to discretize your differential equation in order to solve it step by step. Okay, so if you do that, you have the delta phi, which is just the difference of the two phi infrared. Then you have some drift, and then you have the noise. But actually here you see the noise, the discretized version of the noise. It's this delta W here. It's called the Wiener process. Okay, that's just for the culture. And of course, you can a priori evaluate the right-hand side, and in particular the function of your background at any time between n and n+1, which are the two time steps that you are looking at the evolution between the two. So alpha between 0 and 1 is anything you want a priori. And you know this from the study of ordinary differential equations. Maybe some choice is better for numerical stability or this kind of things. But at the end, the physical result should not depend on the choice of alpha. That's common sense. But well, things are more complicated in stochastic differential equations. And this is what I want to show you, is that although it's irrelevant for the deterministic differential equations, it is actually crucial, the choice of this alpha for stochastic differential equation. So I don't want to just claim it, I want to prove it to you. So let's go into the details. So let's look at how these different terms scale with the time step delta n, between n and n+1. So the drift term is just like in normal ODE, it scales like delta n, easy. But then we have this delta W, the Wiener process, the noise itself. Actually, it is a delta W squared, which scales like delta n. This is something that is due to this white noise here. And therefore, the noise term scales actually like the square root of delta n. So this is something that you may have already heard, is that this Brownian motion, because at the end we are only describing Brownian motion here, is actually a continuous function of continuous function of time. When delta n goes to 0, this term goes to 0, but it is never differentiable. If you do delta W divided by delta n, and you take the limit delta n goes to 0, you find infinity. So this you can see, for example, if you zoom into your Brownian motion, you can zoom as much as you want. You will never be able to define a tangent at any point in this dynamics. So you only have like vertical tangents everywhere, which means no derivative. And the fact that there is no derivative in the Brownian motion changes completely our understanding of these differential equations. Because if you look at the drift term, nothing weird happens. You look at the drift term at the time step n plus alpha, which is the intermediate time step between n and n+1. Okay, you have the one at n plus some correction proportional to alpha, but the correction goes like delta n to the power 3/2. So we don't really care. It's irrelevant. This is like in ordinary differential equations. However, when we look at the noise term, you see that it receives a contribution which is proportional to delta phi times delta W. And because delta W is like square root of delta n, delta phi is also like square root of delta n. And this means that this contribution scales actually like 1 delta n, 1 power of delta n, just like the drifts. So this correction that comes from the choice of the discretization scheme is actually the same order of magnitude than the drift itself. So this is what we call the noise-induced drift, because it effectively acts as a drift. It is deterministic. It does not depend on the delta W anymore, but it is intrinsically due to the noise itself. You see that there is a noise and the derivative of the noise here, and it is proportional to this parameter alpha. So this means that the choice of alpha actually changes the physical result of your resolution of your stochastic differential equation. So this is why in your Fokker-Planck equation, which is the equation for the PDF P, which is the one from which you can derive physically relevant quantities, observables, two-point function, any endpoint function you want, you will have this alpha in the results. That's just life. You have alpha. You need to, with different alpha, you will get different physical results. So let me show you what kind of results you can actually get from this stochastic formalism, because so far it has been completely formal. So I will derive results both in the case of the inflationary universe and in the case of just formally computing quantum field theory things in the sitter. Pierre, you have a question, I think.
Yes.
Please go ahead.
Yes. I was wondering whether this has the choice of this alpha. This reminds me about the Ito prescription and the yes, that one. So
it's exactly that.
Are those the extreme cases for alpha equals 0 and alpha equal 1?
Almost. So you're totally right. So there are different choices, and two have particular names. Alpha equals 0 is called the Ito prescription, and alpha equal 1/2 is called the Stratonovich prescription, sometimes called also the pre-point or the midpoint discretizations. These are these ones, and we will see them again in the next slide.
But I thought I remembered that those didn't have. I mean, that you could choose one of those prescriptions without affecting the physical results. So how is it that? Or maybe I remember badly.
No. Yeah, it's wrong. Actually, what you can do is that you can, I mean, if you start with one prescription, you can always translate it into another one prescription by adding by hand to the equation some noise-induced term. So you can switch from one to the other, but consistently by adding something to the equation. You cannot just choose it like you want.
So what does that mean? Does that mean that we are just looking at, so depending on the prescription, that we are looking at a different field, that we're not talking about the same thing? Because in the end,
I think it means, yeah.
You know, how,
I think it means we are looking at different physical processes, and that the choice of the discretization is actually physical. It means it's not the same process physically. I mean, microscopically, it's different things.
Okay, thanks.
So in the case of the inflationary universe, we can do something which is quite interesting, is to derive the stationary PDF for our scalar field by asking that the time derivative on the left-hand side of this Fokker-Planck equation is 0. So that would be somehow the long time result of this computation. And what we find is pretty interesting. We find that the equilibrium PDF goes actually like the exponential of 1/v. And this small v is just the potential of your scalar field in units of the Planck mass. And this is very weird. It's completely non-perturbative. It doesn't look at all like a Gaussian, like we would expect from cosmological perturbation theory. It's a non-perturbative result. It's something you could not have gotten by means of perturbative treatment. You can also do other things like computing what is the mean duration of inflation. So you look at different patches and you make the mean of the duration of inflation between all your patches. And you can compute this either numerically or analytically with some approximation. So if you assume that the effect of stochasticity is small, and this is measured by this kind of parameters which depend on the second and the first derivative of your potential. If you make this assumption, you can derive some analytical results. And this is, for example, what you can derive for the duration of inflation. Okay, that's just a correction that you can compute. You can also do the same for your power spectrum, and you find also some corrections. So this is a classical result from cosmological perturbation theory, plus some other terms. And this will give also corrections to the famous NSR plot. And therefore, different models, if you take into account the stochastic effects, will be slightly shifted in the space of the NSR plot, for example. And this is perturbative treatment in the sense small stochastic effects, but nothing forbids you to do this in the large stochastic regime. So when these parameters are large, but then you have to rely on a numerical result, but you can still do it. So just a small note, because this is something that was not completely investigated before our work, is the effect of this alpha. Also, Pierre was wondering, is there a physical difference for different values of alpha? Well, it seems that yes. You see the duration of inflation depends on alpha. The power spectrum depends on alpha. So NS and R depend on alpha. But actually, if we are very clear, you see that the alpha here always multiplies V itself, which is a dimensionless parameter, which must be very, 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 very small. And this is in order to be very far from the regime of quantum gravity, where we would have like fields that are trans-Planckian, and we don't want to have this. So actually, the extremely small correction added by alpha is completely negligible here. And at the level of single field inflation, like here, it is completely irrelevant for the physical predictions. So now for results in de Sitter spacetime, we can simplify a lot this equation by assuming that H is actually a constant, and therefore that our scalar field phi is just a spectator field. And we can do the exercise again, and we find a different PDF at equilibrium. And this PDF is still weird. It's exponential minus V over H4. Okay, it is not exponential 1 over V. And but you see that if V is not m square phi square potential, then this is not a Gaussian neither. So it's neither something that can be encapsulated by the usual cosmological perturbation theory. And actually, I want to stress here that what we have done here is actually completely non-trivial. It actually amounts to saying that we have resummed the infrared divergences of our massless scalar field phi. So for this, I want to look at a specific example, which is when the potential is a lambda phi 4 interaction. Then it is well known from QFT in curved spacetime that you have this secular divergences for your perturbations, for your correlation functions. So here, the 2-point function, for example, it is growing with time. Actually, this is a result which is fully general for massless scalar fields. And then if you add this interaction, this self-interaction of your scalar field, you can compute, for example, the one loop correction to this 2-point function. And what you find is some correction which is proportional to lambda times n squared. I'm sorry, I'm just realizing that since the beginning, I've never defined n. I mean, I think it was written somewhere here at the beginning, but n is just the logarithm of the scale factor. So that's the number of e-folds of expansion during inflation. It's a time variable, which is well defined. Sorry for that. And so this result, you can derive it just from QFT in de Sitter, but actually you can also derive it from the Fokker-Planck equation. And which is actually very interesting, in my opinion, is that from the stochastic Fokker-Planck equation, it's actually extremely trivial to derive this result. It's much, much more simpler than doing the full QFT computation. And you find the exact same result with the exact same coefficient in front. So that's something non-trivial. And even more importantly, this is a one loop result in quantum field theory. But you see that if you would like to have the long time value for your 2-point function, what you will need to do is actually to compute the infinite series of loops to resum it, because it is a divergent series. But this is exactly what does the stochastic formalism for you when you ask that this PDF is at equilibrium. So actually, by writing this, you have resummed all the loops here that are never, that have never been computed. Even I don't think even the 2 loop has been computed. So we have resummed all this infinite series of loops in this result with the stochastic formalism, which is quite amazing. So now I want to go really into the heart of our work, which was about extending the stochastic formalism consistently for multifield inflation. And going on, we understood some ambiguities and the problem of discretizations that I have already talked about. So just to be just a little bit of motivation, this is the models of inflation that I will be looking at. So these are so-called nonlinear sigma models of inflation. So they consist in a bunch of scalar fields which are labeled by these letters A that goes from 1 to the number of fields that you have in your model. And I will allow to have some potential interactions for any of the scalar fields. And I will also allow that the scalar fields have some kinetic interactions, so some non-trivial kinetic terms. And this is something which is actually motivated by high energy considerations. So if you look at low energy expectations of quantum gravity, like supergravity that you compactify in 4D or this kind of things, what you will always encounter, almost always encounter, is that you will end up with several scalar fields that they will have a priori potential interactions, and very often they actually also have these kinetic interactions. So this is something which is not only motivated, but it's also the most agnostic thing. I mean, it's just, okay, let's imagine we have scalar fields, they can have kinetic interactions, they can have potential interactions, and all of this is encompassed in these nonlinear sigma models. So then you can repeat the exercise of computing, of separating your fields into infrared and ultraviolet sectors. You can introduce your window function. And if you do so, this is what you find. So now our fields are labeled by, okay, it was A in the previous slide, but it will be I and J in the next ones. So your file I has some drift term, which is again coming from the derivative of the potential. And again, we find without surprise that there is a noise term. But now the difference, of course, is that all this is a bit more complicated. I mean, you have indices, you have to be careful. This noise term is actually a vector now in your field space. And you see that therefore its autocorrelation function will actually be a matrix. So you will have cross correlation of your different noises. So this will be n by n matrix. And this n by n matrix, when you derive what is the statistics of this noise, just like before, you find that it is proportional to the power spectrum of the UV fluctuations at the cutoff scale. So this is very similar to what we had before. Also now we have all the cross power spectra that appear, of course. You can have P1, 2, P n-1, n, etc. And so far, it's just a covariant generalization of the single field case. So now I want to stress a few difficulties. So just let me tell you first that we also have some analytical approximations when the scalar fields are massless. You can have some approximation for this cross power spectra, and they are actually proportional to the field space metric Gij. This is something that is not completely trivial, but that we were also able to show. So first, if you want to derive the Fokker-Planck equation, which is the one from which I derived all these interesting results in the previous case of single field inflation, well, you first need to get off this noise term its amplitude and define this normalized centered Gaussian variable psi that I had previously. But here it is a bit more complicated because now you have to define the square root of the autocorrelation matrix. So you'll have to define the square root matrix. And as you know, square root matrices are not unique. So you'll have to find this square root matrix that we sometimes call Filbine, and I call small g here. And but which square root matrix choosing? It should not that much matter, but we will see that it may not actually be the case. Also, we want to be careful about the covariance of the equations. So just like in general relativity, you want your equations not to depend on the choice of your coordinates to describe the physical processes. It is the same here in multifield inflation. You want to be able to go from Cartesian to polar coordinates if you want, or from Cartesian to spherical coordinates, or whatever coordinates that you want. You want to be able to derive results in any coordinate system without the physical results being impacted by your choice of coordinates. So this is covariance. And we will see that it's far from being trivial here in the context of stochastic differential equation. And this has some links with this discretization ambiguity and the choice of the time grid alpha. So let's go into that.
Lucas?
Yes.
Sorry, maybe stupid. Can you go back one slide?
Yes.
So
I
just,
don't see you,
so
but yes, it's
yes. No, here. So the Gij here, the noise amplitude matrix, when you just call it the same, and maybe stupid. Is not the Gij in front of the kinetic term, is not the...
Yeah, it is. That's the field space metric.
Okay, so it's the same. And
you can show in a massless and slow varying approximation that the cross power spectra of the scalar fields is just h over 2 pi squared times the field space metric. That's an approximation under this hypothesis, but that's an analytical result.
Okay, that's why you put it in. Okay, sorry. Okay.
I mean, it is the inverse field space metric if you want to be very precise. Okay, so okay, let us choose one square root matrix, small g, one Filbine. So far it is okay, arbitrary choice, but we chose one, and we put out of this psi term the typical amplitude h over 2 pi, and now we have defined this psi alpha, which are the Gaussian normalized centered variable. So from this, we can derive the Fokker-Planck equation for the PDF or system of n scalar fields infrared sector of n scalar fields. So we can derive the same Fokker-Planck equation, but for this this multidimensional PDF. So what we find again, without a surprise, is still a convection diffusion equation, but now it is multidimensional. So you see that it is just more general. You have still single derivatives as well as double derivatives. The single derivatives are still quantifying the drift in your system, and the double derivatives are still measuring the diffusion of your system. We will see that there is still some weird features in this equation. So first, you see that the choice of the Filbines, G, so the square root matrix of the noise amplitude, seems to be important because they don't disappear from the result here. So you see that different choices give different results. That's a bit weird. Let's also look at the covariance of this equation. We said that we wanted to be careful about the covariance. Well, actually here, nicely, we have seen the appearance of covariant field space derivatives. And this is just, again, like in GR, you can define this covariant field space derivatives. You need to be careful because you have this non-trivial field space metric. And we see that actually, most of the terms are well covariant. We see the appearance of this covariant field space derivatives. But there remains one term here, which is not covariant at all. You have these partial derivatives, which are not covariant. Thirdly, we see that alpha appears in the results. So the choice of time grid is also important. So, okay, maybe you're beginning to see that it's quite complicated. But sorry, there is apparently two choices of alpha that seem different from the other one, or at least that seem more convenient than the other ones. And these ones are alpha equals 0, for which the second term disappears, and alpha equal 1/2, for which the third term disappears. So let's see these two possibilities. So as Pierre noted, the alpha equals 0 is called the Ito prescription, and the alpha equal 1/2 is called the Stratonovich prescription. So in the Ito case, you are getting rid of the second term in the previous equation. And this is the Fokker-Planck equation that you get. So unfortunately, this equation is not covariant under field redefinitions. You have these partial derivatives that remain. And this is quite bad because, again, it means that your result depends on the choice of coordinates. But you see that the dependence on the field binds actually disappears from the equation because they only appear as a squared. And as a square, this is actually the field space metric, which is completely defined unambiguously. And let me just mention that the lack of covariance in the Ito description is something that people from statistical physics would expect, because actually there is a whole area of calculus which is called the Ito calculus, and which is a generalization of the usual rules of differentiation of functions when you have stochastic processes and when you are using the Ito prescription. And everything gets more complicated. Basically, when you look at the derivative of composite function, you must be very careful. It's not just the usual thing like a derivative of f plus df over d f times the dn, etc. You have this new term, which is proportional to the noise that appears everywhere. And it's actually this term that causes most equations which you would think as being covariant not to be covariant, because this will introduce some non-covariance in the equation. The other choice, alpha equal 1/2, with this respect, seems much better because it is completely covariant. You see that the only derivatives that remains are the nice field space derivatives. So this is very nice. However, there is a dependence on the field binds. You see that the field binds do not just cancel each other in terms of the field space metric, because there is a derivative of the field binds that crucially remains in the result. So, so far, so bad, because no choice seems good. Also, we have no hint from the derivation of which prescription we should use. So that was actually the depressing state in which we were at the end of our first paper on the topic. So now I want to tell you how we solved this problem. And actually, we understood that the Stratonovich prescription was a good one. So the idea is that the ambiguity for the choice of this field binds is completely resolved when you try in practice to do the computation and to compute what is the noise amplitude in multifield inflation. Indeed, if you want to compute the power spectrum of your fluctuations, what you need to do is to quantize them. You have no choice. You must give initial conditions which are quantized. So when you do this quantization of the multifield system, well, you need to be careful. You need to define these annihilation and creation operators, A, in some basis that we label by the number alpha, and which must not be aligned with the particular field space basis in which you begin your computation. There is no particular reason for that. So you end up with some mode decomposition, which is not trivial, which is this phi I alpha. So you see you have n square mode functions at the end. And this basis of creation and annihilation operators is actually constant up to a unique, up to a constant rotation matrix, basically. So you don't have so many choices, if you want, of creation and annihilation basis. So then when you compute the noise amplitude at the cutoff scale, well, what you have to do is to plug this ansatz in your two-point function, use the statistics of the creation and annihilation operators, and this is what you end up with. You end up with the fact that the power spectrum, which is actually the noise amplitude, is just phi I alpha times phi j alpha, sum over alpha. And this is actually exactly what you're looking for. You are looking for something that is the square root matrix of the noise amplitude. And you see that actually, when you compute the noise amplitude, you don't have the choice. You don't have the choice of how to compute it. You need to use the mode functions, which actually are therefore the field binds we were looking for from the beginning. So the mode functions themselves are the field binds, which enable to define this normalized centered Gaussian variable psi alpha. Okay. So you don't have the choice, and which is actually good because it means that you don't have an ambiguity. You just must use the Bott functions phi I alpha. So there is no more ambiguity in the Stochanovich picture, and it is covariant. So this is the one you should use. So now just to go into the applications that you can have.
Okay, I should tell you you have 4 or 5 minutes or so.
Yes, perfect. I will need 5 more minutes. Thank you. So let's look at the Langevin equation that we now understand as being in the Stochanovich prescription. And for this, we will denote it with this circle, this blue circle here. This means that it should be interpreted with a given time discretization. Then, as I was saying before, you can always choose to work with a different time discretization, but then you should add consistently something to the equation, which is the noise-induced drift. If you do this, you can choose the prescription that you want, but therefore it will modify the equation. So for example, we can write this equation, which was in Stochanovich. You can write it in Ito, but therefore we'll have a correction. And this correction, I have incorporated it into the definition of this weird new derivative D. And actually, when you do this computation of changing of prescription, you find that the correction to d phi is this new term, which comes from the noise-induced drift. And actually, this new term is exactly the term that you need in order to define covariant derivatives, which are compatible with the weird Ito calculus that I was mentioning before. So in Ito calculus, you can still define covariant derivatives, but they are different from the ones that we are used to in ordinary calculus, if you want. And actually, when we compute the correction from going to Stochanovich to Ito, this is exactly the correction that we find, which I mean, is like a consistent check, but not that much a surprise because we began from an equation which shows covariant. We end up with another equation which is covariant, but with a different prescription scheme. Let me just mention that from this, we are able to derive new results in the case of multifield inflation. So for example, the 2-point function I was showing before in the case of single field inflation and lambda phi 4 interactions, we're able to generalize it to field inflation when they have these non-trivial kinetic interactions. So you see that the expansion in 1 plus lambda n squared is modified. You have some new term which depends on m here. And m is actually the typical curvature scale of your curved field space. Okay, I'm going a bit quick, I know, but this is basically to say that we have been able to derive some non-trivial results in the theta spacetime for this kind of 2-field models with non-trivial kinetic interactions. And this is something that has not even been computed in QFT because it's too complicated. I mean, because it's complicated, probably it's doable, but complicated. And so I just want to mention that we also have been going in, several other directions that I don't have the time all to present here. But one very important, in my opinion, is to go beyond the approximation of slow roll or overdamped dynamics, where we neglect the acceleration, and to consider the full phase space dynamics. When you do this, you actually don't only have the field space variables, but you also have the momentum that appears. And therefore, you are looking at the whole phase space dynamics. And when you do this, you find noise both for the fields and for the momenta. And actually, you can look at the correlation matrix of these noises, and you have cross correlations of both field, momentum. I mean, you have the thing which is the most general possible. And here I wrote the equation again in Ito, and you see that in order to do this, we had to do the same as before. We started from Stochanovich in order to have covariance. We computed the noise-induced term for the Ito prescription. And in particular for the momenta, I just want to stress that it is quite non-trivial because the momenta are covectors of the field space. This is quite different from the phi I, which are coordinates of the field space. And therefore, the derivative of the covariant derivative of vectors, of covectors, is much more complicated to define. And here we actually found what were the correcting terms that enable to define a covariant derivative for covectors in Ito calculus. And this is something that was not even done before. I mean, it's a bit technical, but it's something that was not even done before in the field of statistical physics. And so, which is for me the most beautiful maybe result that we were able to get, is this very, very general Fokker-Planck equation. So for any number of scalar fields, for any potential, for any kinetic terms, and taking into account the full phase space dynamics. You see that it is fully covariant. You have the appearance of derivatives with respect to the scalar fields that are phase space covariant derivatives. That's very hard to say. And okay, that's just I will finish here and just mention in just one slide, the first part that I knew I wouldn't have the time to present. So it's just one slide to tell you that all these equations, I presented you the easy way to find them by adding this window function in your scalar fields and looking at the equations of motion. But you can actually do it a bit more properly or in a clean way, if you want, at the level of the path integral. So in order to do this, you need to be careful and define your path integral along a closed contour. This is because we are doing cosmology and we are looking at in-in correlations and not in-out transition amplitudes like in particle physics. So you need to define this closed contour in time. And then what you need to do is to integrate out your ultraviolet fields and momenta, which are defined both on the so-called plus and minus branch of your contour. You can do this analytically. We showed how to do it. And then we showed that the effective action that you get by doing that, so you're computing the effective field theory for this infrared modes, it can be consistently expanded in powers of some quantum fields, which are basically the quantum fields, and that the first correction to this classical action is exactly what gives rise to the noise term, which is exactly the one that I have presented before. So this is like a nicer way to derive the same equations with additional features that I don't have the time to go into the details. So I just want to thank you for your attention. I think it's been like 1 hour. Thanks. It was a bit long, sorry.
All right, thank you. Thanks, Luca, for this wonderful talk. And let's open the floor for questions. Please go ahead and ask. No need to. Jakob, I think. That's one.
So it was just clapping, but
sorry.
I have questions.
Oh, you happen to have one.
But I see Pierre, so maybe I let Pierre first.
Or if you raise it, please go ahead, Pierre, and then we move on to Jakob.
Okay.
So my question is very simple. It's I was just wondering whether, so when you faced the problem of the covariance, of the non-covariance of the equations, wasn't it possible to adopt a very pragmatic approach, which would have been to say, I'm choosing a parameterization of the field space such that the metric is locally flat. So a kind of Gaussian parameterization of the field space, do the math. And then once you're there, you just put the covariant derivatives in the way that you get an equation that is covariant. Do you see what I mean?
Yeah, but I don't think it would work because of the following. Because even if the field space is not curved, intrinsically curved, so you can have a flat field space, but still, for example, go from Cartesian to polar coordinates, and still here you would have an ambiguity. Which one should you choose? I mean, why preferring Cartesian coordinates?
No, it's because they are the coordinates in which your Christoffel symbols would be 0. So this is the situation where your normal derivatives coincide with the covariant derivatives. That's just like, but I thought that at the principle, and then I thought, is it actually true that we can do that? And then you'll tell me what you think. But so do we have, is the field space so defined by the phi i's, is it actually a differentiable manifold? Is it actually?
Yes.
It is, because the fluctuations are integrated out, so it should work then. Okay, so we'll talk about that maybe later. But I thought that should work. This is what we do when we don't know what you don't want to do hard calculations in GR. This is what you do, right? You choose the right coordinate system, then you get the results, and then you just you transform the columns into the commas into semicolons, and then you get the result, isn't it? Well, anyway.
Yes, to me it's a bit. I mean, I wouldn't know why to trust more one coordinate system to begin with, because maybe the actual physically consistent coordinate system is one where the kinetic terms are not canonical, and this may make sense. I don't know, in some theories where you have some non-trivial coupling between the scalar fields and the curvature of space-time, for example, and these kind of things. So, I mean, I don't know. I wouldn't be sure of why choosing these coordinates and not another ones. But maybe let's discuss.
If I can comment on this, I can comment indeed, what Pierre is suggesting is called a minimal covariantization. You just go from your flat space approximation into your curved space by assuming a minimal coupling. But if there are non-minimal couplings, as you're mentioning phi with r, that doesn't work. by substituting commas by semicolons, you wouldn't recover the full theory because you're missing this psi coupling phi r, which was not there in the first place when you had r equals 0. So it works if you can do this extrapolation just like you do with electromagnetic fields, but it doesn't if you have non-linear couplings. And in inflation, you are assuming that there are couplings to gravity, which are not necessarily related with a covariant derivative.
Thank you for the comment, making the bridge between the two.
Yeah.
So I think Jacob and then Gonzalo also has a question.
Okay, thanks for the very nice talk. So my question is the following. So okay, when you went to the multifield part, you list the two different approaches again, Stratonovich and Ito. And again, if I understood correctly, the claim is that the one one should pick is Stratonovich, because although has this dependence on so he's the one that is covariant, but he has this dependence on the Weilbein that then you resolve it in you explain it afterwards. So this is something, let's say, basically you choose between the two, given this fact, which is something that you cannot do when you have just a single field, because then there is no.
Yeah, actually, when you have just a single field, it's even more clear that you should choose Stratonovich, because you don't have the problem of the field binds, and you still have the problem of lack of covariance for single field inflation. I mean, even in just one coordinate. So you may think, why is there a problem of covariance? But even in single field inflation, you may want to do some phi go to exponential of phi, for example, or this kind of change of coordinates. And if you want to do this in a covariant way, even in single field inflation, well, you should choose Stratonovich. So actually, I would say that it's even clearer in the single field case that it should be Stratonovich the good choice.
I see. This seems like something at practical level, basically, because so there is an interplane here, which seems very deep between the covariance and the choice of the prescription.
Yes.
And then, okay, you choose one of the two, given the fact that practically is better to have a theory that is well covariant, etc. But I don't see immediately the link between the discretization of stochastic differential equation and the fact that the Fokker-Planck has to be covariant.
Well, you can see it at two different levels. First, the derivation that actually I showed you the result that you get when you do the derivation from the Langevin equation to the Fokker-Planck equation exactly with any value of alpha. This is what you get. So you see that for alpha, which is not 0, not 1/2, sorry, you have this term which is not covariant. So you see the absence of covariance at the level of the Fokker-Planck equation. But you can already see it at the level of the Langevin equation. If you dig into what is Ito calculus, you will see that actually when you do an explicit change of coordinates, you go from phi I to some phi alpha in a different coordinate system. You will see that if you choose actually any alpha which is not 1/2, it's not just Ito, it's any which is not 1/2, you will see that this equation is actually not covariant.
Okay, thanks. And okay, maybe just one last quick one. I don't know if it's quick. So again, this phi bind, right? At the beginning, when you state the problem, you say this, since it's the square root of the Gij, they are not unique. So therefore, therefore there is this issue. And then I haven't fully understood how you solve it in the sense, okay, obviously, I guess you sketch the solution is not the. So basically, you're evaluating this Gij, sorry, the small g on so when you first say that there is a problem because this Gi alpha. The
reasoning is the following: is that you need to define a square root matrix in order to get physical results, such as the Fokker-Planck equation. But now you have a choice between different square root matrices. So you may wonder, okay, but which one should I use? And more importantly, if I choose if I make different choices, will I get the same physical results? Well, the answer is that in Stratonovich, yes, you will get different physical results. So you better have one more motivated than the other ones if you want a square root matrix. And this is basically what I explained, is that actually there is one which is more motivated than the other ones, contrary to what we could sort naively. And this is just the mode functions themselves, because actually you don't have the choice to compute this power spectra. You need to use the mode functions. So there are the field binds that you are looking for. And I mean, you can make other choices, but then you cannot compute the noise if you want. So it's bad choice. So you have only one choice, so there is no ambiguity. That's the reasoning.
Okay, thanks. Thanks a lot.
Right, and I think Gonzalo.
Hi, Lucas. Thank you very much for your talk. It was very, very nice.
Thanks.
My question is a little bit more. So this framework that you showed us, would it be possible to prove or disprove experimentally that the universe follows these models that you suggest? Because, for example, in a single field single scalar field inflation, you can have this consistency relation of the tensor to scalar ratio and all of that. Is there something similar here where you could try to prove and disprove whether the model of this model of inflation is correct?
So I would say that more than a model, it's a formalism to treat models, if you want. It's not really, I mean, I haven't shown you a plot of NSR for stochastic inflation because it's just a way to go beyond the usual treatment, if you want. So for example, I showed some corrections to the NSR plot that you can derive with this stochastic treatment. So I don't think we can really prove or disprove stochastic inflation. For example, if the stochastic corrections are small, I mean, it is indistinguishable from the usual treatment. And if it's not, then it brings correction, but that will basically shift the models in your NSR plane. And maybe some models that you would think are excluded will not be allowed, or some that were allowed will actually be excluded, or this kind of things. Was that your question?
It was along these lines, whether there was some strong consistency relation that you make unobservable, and maybe you have instead of a redshift gravitational wave background, you have a blue shifted or whatever, and then.
So first, this applies really to scalar fluctuations. So that can change the R parameter because it changes zeta, and because R is a ratio of the two, it changes, but that will not change, for example, the spectrum of gravitational waves, the stochastic formalism for the scalar fluctuations. And I don't think you can have consistency relations of stochastic inflation because you can always take continuously the limits where it goes back to the classical treatment, if you want.
Okay, thank you.
And maybe Juan has a question as well?
Yes, it has to do with the generalization of this scenario or proposal, where you have a deviation from slow roll, something that I've been exploring with Jose Maria, as you know. So, of course, there you have a much bigger, you're fluctuating in phase space, as you were describing right at the end of your talk, where not only do you have field fluctuations, but also momentum fluctuations, and they mix, obviously. So the question is, can we covariantize in phase space, not in field space, but in phase space, so that we could write a Fokker-Planck in a super covariant way, including the phase space? Or
that's exactly what we did
in your so configuration space in field space.
So that's exactly what we did. This is a fully phase space covariant. So in the 2n dimensional space, if you want, this equation is a full phase space covariant Fokker-Planck equation. Yes, that's possible. So in particular, you see that this d phi, this covariant d phi, they actually include derivatives of phi and derivative of pi. They are really the phase space covariant derivatives.
Okay, so you have a covariant description of phase space evolution, right?
Sure.
So at some point, we must have some deviation from what you would expect. I mean, you cannot do this. You can do this stochastic field theory, of course, classical statistics, but not in quantum mechanics because of the quantum uncertainty principle. So what are you giving up when you move from covariant field space to covariant field space? Phase space. When you take both fields, somehow there must be commutation relations between fields and momenta, which should be reflected somewhere in this.
Yes and no. I mean, they are there, but they are neglected in this treatment, exactly because we are looking at scales which are at this cutoff scale or higher, this K sigma minus 1.
They're not quite neglected. No, you can neglect the fluctuation of one field with fluctuation of another one at different times, or one momentum with another one, but not field with the momentum at the same time.
Yes, I fully agree. Actually, I fully agree. Actually, in this cross correlation, you will have the field momentum, the per spectra, and these are actually completely fixed by the commutation relations. I mean, they are what they are, but they are actually imaginary.
Yes.
They are imaginary because of this commutation relation. And actually, this is something, thank you for asking the question. It is very non-trivial, the answer.
Yeah.
This is something that we added to the understanding by doing the path integral derivation, is that actually here I've been a bit sketchy, but what really appears in the noise statistics is not the polar spectrum. It is just the real part of the polar spectrum.
Okay.
So actually, the imaginary part of the polar spectrum disappears from the noise statistics. And in particular, the effect of the commutation relation is just not there anymore.
So where does it go? I mean, it must do something with the computation of probabilities, right? It must introduce some.
I would say it's
loss
lost.
Of information.
I would say it's lost
Yeah,
in this classical stochastic treatment. It's lost, I would say. But I mean, it kind of makes sense also because although it is there, it is quickly decaying on super horizon scales. This commutation relation.
So
it's there. Yeah. It's not zero. You're right, but yeah. I mean, it's decaying quickly, and I mean, an approximation is that we are looking at super horizon scales. So I would say it's just there in the assumptions of the formalism.
But somehow you must keep your correlations, even if they're on super horizon scales, right? Imagine that those fluctuations re-enter again into the horizon. There are non-trivial correlations among fields at different points in space. Because of this, there is some kind of entanglement. You haven't completely eliminated those. It's true that on many e-folds beyond horizon crossing, it's exponentially suppressed. Those terms are exponentially suppressed, is what the stochastic inflation tells us. But eventually, when you re-enter, those correlations, entanglement is still there. So you can look for them in higher order correlation functions, not just in the power spectrum.
But then they were going in, I guess, right? You know, if they want to include those, they would use the in.
I think I agree with you, but I think I agree with you. But the confusion is just that it is not taken into account by this formalism. And I know there are. I mean, this is one formalism for treating the large-scale fluctuations non-perturbatively, but you have other ones. You have the density matrix approach, and you can look at the non-diagonal terms in this density matrix, for example, which I think have something to do to this with this entanglement. I think they are decaying with time, but they are non-zero at any time.
Formalism,
So that's other approaches that may encapsulate better these quantum effects, which I think are lost in this stochastic formalism.
Okay, thank you. That was a very nice talk, Lucas. I enjoyed it.
Thanks.
I think with this we can stop recording because we run out of questions. Let me what is it? Oh, there it is.